So hello, welcome back from break. Today we are going to start up chapter 30, which is quantum physics. I'll be honest, this was actually my best subject in school, so I'm kind of always happy to teach it. Um, but it is a little weird. Quantum physics is the way we think about most physics when you get down to it these days, but a lot of things that just don't make sense have to be true for quantum physics, or at least won't make sense on a macroscopic scale, like we're used to working with. That can happen on the microscopic scale of single electrons. Before we get into that, though, let's just talk about we got 2 weeks left plus finals. So here's the setup. The setup. Here's the setup. This week I'm going to do chapter 30. Your lab 12 will be due, and I'll open lab 13, and your homework 29 is due. Next week, we'll do chapter 31. Your last lab will be due. Homework 30 will be due. And sometime next week, I'm going to do a review session where I'll go through last semester's final. What day I'm going to go through last semester's final, I sent an email about that this morning. There is a poll in Banco Hall. I'll see what you guys all say, do what time works best, and post it online. I went through a lot of the details about how the final is going to be on Wednesday's class, where I talked about the format and things. If you want to look at that, you can check that video. Dear God, I sound like a YouTuber sometimes. Check this video. Anyways, as for after that, your last homework is due on the Sunday before finals because I'm an asshole, but I have to have it due sometime. Your final is on Monday from 5:30 to 7:30 p.m. I hope to grade it by that Tuesday. And that's the general setup for the end of the class. Of note, my office hours 1 week from today, I have to move them. But yeah, that's the setup going forward. Any questions about that for the few people in the room?
Nope.
Okay.
Does it say the final is in February, or is that supposed to be?
Yeah, nope, there's a lot of ones missing there. Do. You're good. Sorry about that. Yes, those are December 14th and 15th. Thank you. Yeah, I fail. I have no better explanation. Makes me wonder if I had that mistake in my other class too, because I put this up in a different class. And no one commented then. I have to go look. Okay. Other than that, let's get into quantum physics. From last chapter, we now know that at very high velocities, the world is very different. That length and time kind of lose meaning when you go fast enough. And the general idea is if you look at things small enough, the same is true. Classical physics, when we talk about energy and how many joules of energy something has, it can have any value anywhere in between. But people learned that in very small spaces, like singular electrons and whatnot, that energy has discrete values and is not continuous. And also the whole idea that a light can act like a particle or a wave, that everything can. In between the 1900s and 1930s, a bunch of physicists started working on it together. And a whole bunch of basically rethinking the entire way physics works. This chapter, I'm going to talk about all of the people there except for Polly. I just kind of found a picture with enough people and I used that one. Polly will come up next chapter. But it's a group of people who kind of worked together and revamped physics. In fact, there's a very famous photo. Oh, yeah, I just saw it. And going back, I just love this news bullet quote. This is about what we're about to cover. If you're not shocked when you come across it, you couldn't have understood it. That's what we have to look forward to this chapter. Isn't it exciting? But yeah, there's this very famous photo. This is from the Solvay Conference of 1927. And this conference is kind of the birth of quantum mechanics. All of last chapter, relativity, and all of this chapter is part of what is called modern physics. That's because classical physics was made long time ago. And this, which was approaching 100 years ago, is very modern compared to the most of physics we talk about. And as I said, all these people were kind of discovering it all together around the same time as each other. And so, just to give some names, a bunch of people we will talk about throughout this chapter. For example, right here is Schrodinger. He is the one who made the wave equation that describes all quantum physics, which we will cover later on in this chapter, also famous for the Schrodinger cat thought experiment. Over here we have Pauli. He made something called the Pauli exclusion principle. We'll cover that next chapter. This right here is Heisenberg. He got a Nobel Prize in 1932 for the Heisenberg uncertainty principle. I'm not going to cover everyone, just the big ones. This is a man named Leon Brillouin. The Brillouin zones is kind of the basis of all semiconductor physics. We got Bragg. Bragg was discovered Bragg's law of X-ray diffraction, also known as Bragg scattering. We will cover it this chapter. This right here is Max Planck. Planck is probably the most important person here. We're going to talk about him quite a bit, and we've already talked about him a tiny bit with the Planck's constant was mentioned in passing a few chapters ago. He is the guy who started quantum theory. Right here we got Curie. She is the first woman to get a Nobel Prize in a science, and she is also the only person to get a Nobel Prize in 2 different sciences, having won a Nobel Prize in physics and a Nobel Prize in chemistry. She termed the phrase radioactivity, discovered elements, and basically worked out everything about radioactivity, although she did die from excess radiation poisoning. She's not going to be covered in this. She's mostly chemistry, but it's just kind of neat that she's there. This is Mr. Lorentz, or Dr. Lorentz, really. He was a mathematician, and he worked out something called the Lorentz transformation. That is the basis of Einstein's general relativity. He also worked out the Lorentz force, which you might remember from a few chapters ago. That's dealing with magnetic fields. We got Paul Dirac. He made the Dirac equations. This is the guy who first predicted antimatter could exist. We got Einstein. You know who he is. We're going to talk about him a lot more this chapter. This is good old Compton. We're going to talk about Compton a lot in this chapter too. De Broglie also talked about a lot this chapter. He's the first person that said atoms. Electrons can work as waves. And I'm jumping all the way to Niels Bohr, who proposed the Bohr model of the atom, which we're going to talk about next chapter. And it's how most people like to view the atom, although the Bohr model of the atom was disproved a few years later by Schrodinger, who once again was, that's not what I want, who once again was right here. So he had a model of the atom till this guy disproved it. But it still gave us a lot of understanding of physics. So all of these people that we're going to talk about this chapter and next chapter were all alive at the same time working together. Quantum physics really grew in a small 5-year period to explain how everything works. And I mean, there's still more happen with time, but it's kind of crazy that it was one group all at once. And everyone else here who I didn't name, they're all famous for various things, just not as famous. So to talk about quantum physics, we got to start with why people started looking into it. And that is something called blackbody radiation. We covered blackbody radiation physics 1, although I didn't use that term. We covered radiation in general, thermal radiation. Anytime everything that exists is radiating electromagnetic waves. And it radiates electromagnetic waves based on their temperature. If something is at, the temperature will affect the wavelength and the frequency of the light. Something at room temperature will radiate light in the infrared. Right now, you are radiating light. It's just infrared. You can't see it because you can't see infrared. Infrared goggles, the night vision goggles, how they work is they look at the infrared you put out. If you heat something up hotter, the wavelength that is produced will shift. And you get something hot enough, it'll start glowing red. You heat it up even more, it'll start glowing white or blue. Now we know white is a combination of all colors. Things glow white because it's going to be emitting red light and blue light at once. But you get really hot, you might get it to emit blue light. Really? At all temperatures, everything radiates all wavelengths. It's just the majority of the wavelengths. Right now, you're emitting some visible wavelengths too. They're just really, 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 really dim. And likewise, when this is emitting red, it's emitting some blue light also, just not as much. This is actually the basis of why some stars look different colors. That like Orion, Vigo in Orion looks blue, and Betelgeuse in Orion looks red, just because they're very different temperatures. Now, classical physics said the reason for this, the reason that when you heat something up, it glows red, and if you keep heating it up, it glows blue. They said the reason why was that accelerated charged particles cause the radiation. That if you heat something up, the electrons in it will accelerate. When the electrons in it accelerate, they start moving. When electrons are moving, that's going to create a moving electric field. A moving electric field creates a moving magnetic field. And a moving electric field and magnetic field, that's light, like we covered a few chapters ago. But this didn't explain what was called a black body. A black body is an ideal system that absorbs all radiation that hits it. And to make a good approximation, take a sphere, and this just looks like a circle, but it should be a three-dimensional sphere, and cut a very small hole in it. And sorry, a hollow sphere with a very small hole in it. If you shine light in, chances are no light will come back out. Because if you shine light into this, it's going to go and bounce off the inside, and bounce off the inside, and bounce off the inside, and bounce off the inside. And for it to come perfectly back out this small hole you made is pretty slim. Now, logically, if you do this, though, how much the radiation that comes off this black body, if you're shining light in it, you're giving it energy. There has to be some sort of, it has to stay as a sort of, energy has to be conserved. That it should matter how much radiation comes out, depending on the shape and the material and whatnot. And what they saw is that since everything radiates, if you shine light in, if you start messing around with the light you shine in, it should change the radiation. But what people found is the radiation that something emits only depended on temperature. That what temperature something was, that was it. Nothing else mattered. And this didn't make sense. You see, if you look at the experimental data for distribution of energy, what we see is that at a lower temperature, and you gotta like how this graph says has a lower temperature being 4,000 degrees Kelvin, but whatever. At a lower temperature, it's going to be emitting lights from 100 nanometers to up to like 2,000 nanometers, and then a bit of everything. And as you increase the temperature, what happens is the intensity increases. But as the intensity increases, the peak shifts towards the blue. And so at like 1,000, you're going to see red light because you have very little blue light, very little green light. You know what? Let's put on my pen. Very little blue light, very little green light, a bit more red. You'll see mostly red. You heat up enough, like 5,270 Kelvin, the peak shifts to the left quite a bit. And now we have the entire section of visible light in here, you see white. If you keep heating it up like 7,000 Kelvin, this peak is going to shift further to the left and upwards. And now it's going to have a lot of blue light and some yellow and red, but there's so much more blue light, the blue overtakes it. And what they found is that the peak wavelength, what value is the highest bit on this curve, goes by Wien's displacement law. I like how I capitalize the L and not the D. That's the D should be capital too, which is that the peak wavelength times the temperature goes by a constant, 0.2898 times 10 to the negative second meters times Kelvin. So this is one of those things that people worked out that this equation worked. People didn't necessarily work out why. It's one of those, hey guys, if we say this is true, all the math works and no one knows why it's true. But it does match that as you increase the temperature, this gives exactly where the peak wavelength is. But here's the thing. And here's a different version of the same figure that kind of shows it in color. If you do this equation, this Wien displacement law, logically, it should keep going forever. The higher the temperature goes up, the lower the wavelength goes up. And it should infinitely keep going. And also, it should infinitely keep getting more and more intensity and more UV. And that doesn't actually happen. There's actually a limit. Classical physics doesn't quite match. And in fact, if you try to take something like the Wien displacement law, it should say that at 5,000 degrees, the temperature just kind of goes up and has a peak really, 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 really high, kind of off the graph. But in reality, the peak is much lower, and it doesn't shift as far as it should be assumed. This violated everything people knew about physics at the time and was called the ultraviolet catastrophe, because it's just like, well, we know everything we know must be wrong. Why? Oh, but it must be wrong. And in the year 1900, Max Planck figured out why. As I said, we mentioned him in passing. He is about how light can be a particle, but we'll get into it now. What he said, I'm going to actually read from my slides for once, is Blackbody Radiation was produced by submicroscopic charged oscillators. What he means is he said that all this blackbody radiation is because of very tiny particles oscillating, and he called them resonators. And he said that that the resonators have a discrete energy. Well, the energy of the resonators is NHF. Well, N is an integer, H is Planck's constant, because when you make the equation, you can name the constant after yourself, and F is the frequency of vibrations. And he kind of said, hey, if this is true, it all works. Now, this was a crazy idea, that the energy was quantized, that the energy could be at very set values, but not in between. Yeah, there's going to be a bit of history lesson with this chapter. And this was a completely new idea at the time, the idea of quantizing your energy. He said that the energy could be HF, 2HF, 3HF, or so on. N could be any integer, but it could never be 1.5 HF, 2.678 HF, pi HF. It could only be integers. This is the idea that if you wanted to place a ball on a ramp, you can put it anywhere. You want to put a ball on a stairs, it can only be on one of the steps. It can't be in between. And yeah, that's what he said. And so a lot of people, the question is, okay, that's cool. It's quantized. Why do you think that? To which Planck had one of my favorite responses ever. I don't know the exact quote, but the general idea of, oh, Planck found this equation matched the data and had no fucking idea why. His reasoning of why these resonators existed and why that equation was it was because the math worked. And he actually kind of made it his life goal to figure out why the math worked and why it was true. He didn't, in the end, work it out. Einstein did, but, he did get to live to see it worked out, being that, once again, he's right here, Einstein's right there. They got to at least meet and when it got worked out. How Einstein worked it out was by looking at something different that we haven't talked about yet, called the photoelectric effect. In the latter part of the 19th century, people realized that if you shine light on a metallic surface and you take a hunk of metal, take a other hunk of metal, and put a wire connecting them and shine light at one of the pieces of metal, you could create a circuit. And so what this is showing here, right, is that there's a hole in the first one. So this blue line's the light. When the light hits the emitter, the plate's called the emitter, it emits electrons. The electrons fly over to hit C, the collector. As the electrons hit C, they have now a chain. It's basically like a big capacitor. They have a charge because we lost electrons from the emitter. They went to the capacitor. That's going to be a circuit. And we can measure the voltage and the current through it. I'll get into why the variable power supply is there in a second. People understood the photoelectric effect. They knew that in the dark, there'd be no current. And if you shined light a current would go even if there was no power supply. What people often did is they hooked up a variable power supply, and they would put the power supply pointing in the opposite direction of the current of the voltage that was caused by the photoelectric effect. And you're going to do this in lab this week. And you then, if you, whatever voltage leads to zero current, that's the voltage of this setup. But people saw that when they shined light, they got a current. But they only got a current if the light they shined had a shorter wavelength or a higher frequency than a set value, with a value dependent on what material it was. For the record, photoelectric effect still pretty heavily used. If you have an electric garage door, there's little sensors at the bottom. So if the door is closing and something passes through, it stops. That is the photoelectric effect. Like most Nintendo things, like the Wii U, nunchucks and stuff, the Switch doesn't have this. No, the Switch does still have IR things on it. Those also use the photoelectric effect. Basically, anything you shine light on and therefore you get current, that's the photoelectric effect. Now, what people also knew is that if you increase the voltage of this power supply, the current increased until it hits a maximum value. And you could change the max value by adding more intensity light. That the brighter the light is, the higher the max value could go. But if you make the voltage go negative, have it go against the current goes down since the electrons are repelled by the plate. Basically, you're putting a battery in backwards in the circuit, you can eventually stop it. And so people said, okay, if we have the voltage at zero, it's going to go up to a peak. If we add more voltage, we can get more current out. But if we bring it negative, we can get it to zero. But at 0 volts, we have a current. Now, that current that the voltage goes to zero, that is known as the stopping potential, because that's where you stop the electric potential. And they found that the stopping potential was independent of the radiation intensity, aka is independent of the light, how bright the light was. That with high intensity light or low intensity light, it didn't matter. The stopping potential was the exact same thing. They also realized that the maximum kinetic energy of the electrons, aka how fast the electrons went from the emitter to the collector, was related to the stopping potential. That the max kinetic energy of these electrons was the charge of one electron times the stopping potential. Now, classical physics could not explain A, why no electrons were emitted below a certain threshold frequency, B, why the max kinetic energy did not depend on the intensity of the light at all, C, why the max kinetic energy increased with increasing frequency, and D, why the electrons are emitted even if the light is very dim, that the intensity did not affect it. The only thing intensity did was you could go, if you added voltage, it could add to the current, but that's it. But it did not change the kinetic energy. And this was explained in 1905 by Einstein. This is what Einstein got the Nobel Prize for. This is what made him famous. So this is pre-relativity. And what he did is said, hey, that stuff Planck said, I can explain it. And said the reason Planck's equations worked is because tiny packets of light energy, which were eventually known as photons. He did not give the word photons. That didn't come for, like, what year he was 19? I already forgot what year Einstein stuff was. 1905. So 15 years later, the word photon came out. But he said tiny packets of light energy are emitted whenever Planck's quantized oscillators made a jump from one energy state to another energy state. Well, each energy state will have an energy of NHF following Planck's equation. And if it drops from one value of n to the next lowest, which is just n minus 1, it'll release one of these tiny packets of energy. I'm just going to say he said photon, even though it didn't come 15 years later, just because it's going to be easier to say photon. And he said conservation of energy says if it goes from NHF to N minus 1 HF, the energy of that photon must be HF. And the energy lost by the emitter stays localized. And that energy can transfer as a packet. And so when you shine light onto the thing, you are adding energy. You are adding energy of HF. What he then says is when this packet of energy hits the metal plate, it imparts the energy. And basically, when they hit the metal plate, they impart all of this energy into the metal. When the energy is added to the metal, it'll cause electrons to fly off. That basically we're shooting it with a rail gun and pieces are chipping off and flying away. And as we add the energy, the electrons shoot off and start moving. Some energy will be taken just to rip the electron off, and the rest of the energy would go towards kinetic energy, making it moving. And this was why he said there was a threshold frequency. See, the frequency had to be above a certain amount because you needed enough energy to remove the electron. If you didn't have enough energy, the light would shine on the electron would be cool. It's hotter now. But you put enough energy in, you'd launch the electron off. And he said the max energy from the emitted electrons would be HF minus psi, where psi is the work function. Where he said the max kinetic energy would be the frequency of light you emitted, the frequency of light you shined on times Planck constant minus some constant. And this work function, the work function is just a way of saying how much energy is needed to pry off the electron. And so it's saying if you want to launch an electron off, you need to add enough energy to rip the electron off, and then enough energy to make the thing move. And therefore, if you rearrange this, right, it's HF equals KE plus the work function. It says the energy that you impart with one photon, the energy of a photon being HF, will be the energy to remove an electron, the work function, plus the energy the electron gets, which will be the kinetic energy. And so when you shine light on this metal, if you have enough energy that it's above the work function, you'll rip off the electrons and fling them from the emitter to the collector. And if you start flinging electrons from the collector to the emitter, I'm going to go back for a second, that's a circuit. They'll start coming off here over to that. Any questions there so far? Because this is kind of crazy.
What is phi again?
The work function. So the work function is the minimum energy required to rip the electron off. Now, I didn't stress one thing. The energy required to rip one electron off, the work function, is kind of small. And for this reason, it is often displayed in units of electron volts. Electron volts is the amount of energy one electron has accelerated with 1 volt. And in general, 1 joule is 6.24 times 10 to the 18 electron volts. You would normally see the work function given in EV. If you're given stuff in EV, you're probably going to need to convert to joules. But there's the conversion. Any other questions?
No.
Now, the reason this crazy idea, which doesn't seem that crazy now, saying if you add energy to something, the amount of energy you add is how much energy the thing gets. But this was really crazy because this was saying light is a photon, light is a particle, light is not a wave, which once again was the common belief at the time. People had started to realize that it's possible that light is not a wave, which we talked about earlier with the did I? Yeah, I've already done the Michelson-Morley experiment. I did that a few chapters ago. But this was the logic behind it. And see, Einstein said, if this is true, this gets rid of all of our issues with the photoelectric effect. So, why were no electrons emitted below a threshold frequency? It's because the emitted electrons are from the absorption of a single photon. So the energy of the photon must be greater than the energy to remove an electron. Why did the max kinetic energy not depend on intensity? Because intensity has nothing to do with energy. The kinetic energy is the energy minus the work function, and the energy doesn't care about intensity. Why did the max kinetic energy increase with frequency? For the same reason. Why are electrons emitted at even low intensities? Once again, we don't give a shit about intensity. We care about the frequency. And it also happens because the photons, if you changing the intensity, just means you change how many photons you shoot. The photons move at the speed of light no matter what. So even at low intensities, you still have something coming and hitting hard. And it's hitting hard enough to rip off electrons and send them flying. Now, we making sense so far?
Yeah.
Using all this, we can talk about the cutoff frequency. The cutoff frequency is the minimum frequency of light needed to make the photoelectric effect happen. Because as we said much earlier, jump to this one, is that, no, it wasn't there. I mentioned it at some point. I forget where I mentioned it though. I'll just keep going. As we said earlier, and I'm just going to go with it, is that the light only happened. The circuit only existed. We only had a current when we had a frequency above a certain amount called the cutoff frequency. What we can say is that is the frequency that will give enough energy to match the work function, aka enough energy to remove the electrons, but not necessarily give them any kinetic. What we say is if the kinetic energy is 0, that is going to be the minimum frequency required to remove electrons from this piece of metal. And so F of C will happen when Ke equals 0. Which means if I add the work function to both sides and divide both sides by Planck's constant, we can say the cutoff frequency, the minimum frequency required to make the photoelectric effect work, is the work function over Planck's constant. Now, some things to be careful with here. I have always given you Planck's constant in joule seconds. There was also a version of Planck's constant in electron volt seconds. I did not introduce that version of Planck's constant because I didn't want to get confusing and using multiple units. So if you're given the work function in EV, make sure you convert it to joules. Also, most of the time when people talk about light, they talk about the wavelength, not the frequency. The frequency is what we care about. But, I can say something is, this laser pointer is 450 nanometer wavelength light. I have no idea what its frequency is. I could solve for it. We know how to solve for it, but I just don't know off the top of my head. If you ever want to find the cutoff wavelength, just remember that for light, wavelength times frequency is the speed of light. Which means the cutoff frequency is C over the cutoff wavelength. But don't forget the cutoff frequency is the work function times H. And with a bit of rearranging, you can say the cutoff wavelength is Planck's constant times the speed of light over the work function. And these two equations will tell you for the photoelectric, what is the cutoff frequency, what is the cutoff wavelength. So, going back to the garage doors. Sorry, I'm looking out my window at my garage, not that it helps you. There's a little sensor on the bottom, right? And if your garage door is going down and you trip it, it makes the garage door stop. The reason why is it's shooting light with a frequency higher than the cutoff frequency across. And it's going from one side to the other. When it goes from one side to the other, it's hitting something and causing a little circuit. The electrons aren't shooting all the way back around your garage door. It's just a little circuit on the one side. But the light coming across goes. The second you step in front and block that beam of light, which is infrared, by the way, you can't see it because it's infrared. But once you block that beam of infrared light, you stop the circuit. By stopping the circuit, garage door stops because it's only there when the light is shining on it. Same idea of an old, like a calculator with a photocell that you have to be in the light to use. Light is hitting it, that is creating a circuit. If you're in the shade and it stops working, it's because light's no longer hitting it. You don't have the circuit. That's how most that type of solar panel works. Something that isn't storing energy. That's the basis. Okay. Let's do an example problem. The longest wavelength of photon needed to knock electrons out of a metal is 700 nanometers. What is the work function? And B, if a 400 nanometer light hits the same metal, what's the max kinetic energy of the electrons? So I'm saying longest wavelength is 700 nanometers, or 700 times 10 to the negative 9 meters. If that is the longest allowed, that's the cutoff wavelength. Now we know H, we know C, and we can say that the cutoff wavelength is HC over the work function. That means the work function is HC over the cutoff wavelength. And there you go. That's the work function. The work function of this thing is 2.84 times 10 to the negative 19 joules. Now, if you want it to be normal, you could convert it to electron volts, but that's just a conversion. What this means is if the energy hits this thing is less than 2.84 times 10 to the negative 19, nothing happens. If the energy that hits it is higher than 2.84 times 10 to the negative 19, you're going to get the photoelectric effect. It's going to emit electrons. You're going to get a circuit. Part B says, what's the kinetic energy at 400 nanometers? You want the kinetic energy at 400 nanometers? I didn't give you F, I gave you lambda, but keep in mind that F is C over lambda. So I can just plug that in. I'm going to stick to using joules here and not EV for the work function. And there you go. This is how it works. This is the basis. This is the basis of all quantum physics, that everything that is quantum physics is based off this idea. Because this said that the energy is quantized. If the energy of electrons are quantized, if the energy of the light is quantized, the energy of everything else can be quantized. And next chapter, we're going to go into models of the atom from a physics standpoint, not a chemistry standpoint. What that's going to say is that all of that's quantized too, using this same logic. That this explains why the model of the atom is quantized. And if the model of the atom is quantized, everything is atoms. That means everything is quantized. It all comes from here.
Just a question.
Yeah.
So garage doors work on this principle, but do like automatic doors at grocery stores work in the same way, or do they do something else involving the light?
I don't know off the top of my head because there's a lot of different ways to do it. It would make sense, but because the general thing is when something gets close, the door opens. I wouldn't be
Yeah, like it's
surprised
more
if
of a
there's a sensor
proximity.
further back. And so when you pass through, you block the light, you stop the circuit. When you stop the circuit, it has something triggered. So when the circuit stops, it opens.
Okay.
But I don't know for sure just because I don't happen to know that setup. I've never actually looked around for the sensors, to be honest. I'd have to look it up, but I wouldn't be surprised if it's the same.
Okay.
You'd either have to do that or have fun with putting like a weight detector on the ground underneath, so when you step on it, it triggers, and that's not going to be a thing that happens. So I would assume it probably is it. And once again, it would just be a beam of infrared light that's being shot across. You step up, you block the beam of infrared light. It stops the circuit, which triggers the door moving, but you can do that with circuitry. That's not impossible.
Yeah.
Most anything you interact with by not touching is normally this. It's normally a beam of infrared light. Once again, this is going older with the systems because I think of the Wii over the Switch for this, but this is that's how the Wii worked too. That the little Wii detector ball just was an infrared light source, and it could tell which way you were pointing because where the infrared light was hitting it.
Okay. That makes sense.
Okay. To simplify this a little bit, just a little bit, Einstein said that light was quantized and was consistent of particles. The light was not always a wave. Each photon of light has an energy of hf. Planck's equation, which was nhf, was because you can have an integer number of photons. One photon, hf. Two photons, 2hf. Three photons, 3hf, and so on. That was why his equation worked. This means energy is proportional to frequency. It does not depend on intensity. Red light is low frequency and high wavelength, so lowest energy. Violet light is high frequency, low wavelength, so high energy. And this also is partially because it all moves at the same speed, no matter the wavelength. That if this blue one with its tiny little jumps wants to keep up with this red guy with these huge steps, he has to move a lot quicker. He has to jump a lot quicker, must have a much higher frequency, must be more energetic because it has to go at the same speed. And I will end where I end. Do I want to do that today? Okay. Yeah, I'm probably gonna end a little early. I kind of want to go a little bit further, but it's one of those things that I'd start the topic and there's no way in hell I would finish the topic. But I should be far enough. With one more quick example. That says, let's say I got a photon of red light. Red light has a frequency of 5 times 10 to the 14th hertz. How much energy is that photon? You want the energy of the photon? HF. H is a constant. You plug in, you get it. Now, your lab that is being released this week, not the lab due this week, but the one released this week that you're going to do, that is due next week, you're actually going to measure Planck's constant directly. And you're going to measure Planck's constant directly by using the photoelectric effect. You're going to shine light of various frequencies on something and measure the cutoff voltage. It is a very measurable, usable thing. This has all been proven. So I'm really torn if I want to start this topic to make sure I don't run out of time. No, it's better I stop here. It's better I stop here and don't start a topic and don't finish it. I think I should have plenty of time on Wednesday to finish. So we're in there. I'll talk to you on Wednesday. Hopefully you can tell I get kind of excited teaching this topic. I think it's really neat. Hopefully you at least find it somewhat interesting. I will look up that thing about doors. I assume that's why, but once again, I'm a physicist, not an engineer. But I'll look into it. But other than that, have a good day.